I want you to take a second right now and just think about all the invisible decisions that have already been made for you today, like just since you woke up.
Right. There are probably hundreds already.
Exactly, hundreds. Think about the exact dynamic pricing algorithm that figured out what you paid for your morning coffee on that rewards app. Or, the hyper-specific real-time bidding war that happened in like literal milliseconds to serve you that one particular ad while you were scrolling your feed.
Oh, yeah. Or the routing logic your GPS used to steer you away from a traffic jam before you even knew it existed.
Yes. And to most of us, navigating this world, it feels incredibly seamless. It feels almost biological. I mean, like the technology is just anticipating our needs and organizing the physical world around us.
It feels like it's thinking.
Right. But if you strip away the sleek UI and, all the machine learning marketing buzzwords, you aren't actually dealing with a digital brain. You are dealing with an architecture of microscopic forks in the road.
Billions of them.
Yeah.
Billions of them executing in parallel across distributed systems. And what's truly compelling when you look under the hood is that every single one of those forks, every decision point that shapes this whole digital infrastructure, it relies on a logic that is uncompromisingly rigid.
Like completely inflexible.
Completely. It doesn't intuit anything. It doesn't infer context. It just executes literal instructions at a speed that creates the illusion of intelligence.
Which is wild. So today we are doing a deep dive into the architecture of these decisions. Specifically, we're looking through the lens of a foundational visual language called Coral, which maps out how a machine actually processes logic.
Yeah, the flowcharts.
Right. We were going way beyond the basic idea of a computer just answering yes or no. We really want to get into the mechanical reality of how computers evaluate truth, how they navigate these incredibly complex nested rule sets, and how the physical limitations of the hardware itself fundamentally alter the math we rely on. We're talking about the deep architecture of branching logic.
And it's such a crucial shift in perspective because we naturally tend to anthropomorphize our devices.
Oh, for sure. We yell at them like they're people.
Exactly. We assume they are, thinking through context. But understanding the exact mechanics of execution, the literal step-by-step evaluation of Boolean expressions, it gives you this profound appreciation for both the fragility and the sheer power of the technology we rely on. I mean, it's not magic. It's deterministic architecture.
So by the time we wrap up this deep dive, you're going to look at everyday systems like automated hotel pricing or the triage menus on customer service calls, even the toll booths you drive through.
Yeah.
You're going to look at them with X-ray vision.
You'll see the matrix.
Yeah, you'll see the implicit boundaries, the cascading logic, and the hardware-level compromises that actually make them function. Because I'm fascinated by this dichotomy. We build these staggeringly complex systems, right? Global financial networks, autonomous vehicles, and they all ultimately rest on a bedrock of like glorified yes or no questions.
But that simplicity is precisely where the power lies. The complexity we experience, it isn't derived from any single complicated question. It's derived from the scale and the velocity.
Right.
A CPU's ability to evaluate millions of simple conditions like true or false, path A or path B in a fraction of a second is what allows for complex emergent behavior.
Right.
Like, if the fundamental building block wasn't that brutally simple, the system couldn't scale.
Okay, so let's start with that fundamental building block, the fork in the road. In architectural terms, we are talking about a branch.
Right.
For anyone who writes code, the if-else statement is, second nature. But looking at it through the Coral visual models we're studying today, you see it as a literal diversion of flow. You have a condition, usually represented as a diamond shape, and the execution path literally splits.
Yeah. The execution path, which is just the sequence of instructions, the processor is actively running it. It's a conditional instruction.
Yeah.
It has to evaluate a Boolean expression. And since we are assuming our audience here knows the basics, we don't need to belabor what true or false means.
Yeah, they get it.
But architecturally, what's actually happening is a physical jump in the instruction set based on that Boolean evaluation. If the expression resolves to true, the program counter-jumps to the memory address for the first set of instructions.
And if it's false?
If false, it jumps to the else block.
Yeah.
Or, sometimes there isn't an else block and it just skips the true branch entirely and moves on.
Let's contextualize this with one of the models from the source material, dynamic pricing for car insurance.
Oh, this is a great example.
It's a perfect example of translating human risk into a rigid binary fork. The model sets up a very basic conditional check on a user's age. So the input is age, and the diamond evaluates is the age less than 25.
Right.
If that Boolean expression resolves to true, the annual price is set to $4,800. But if it's false, meaning the driver is 25 or older, the price drops to $2,200.
That is a massive difference.
It's life-altering, a massive financial difference based on a single integer threshold.
It is. And, the underlying actuarial data in the text explains the harshness of that threshold. The models cite 2025 data from the Insurance Information Institute, indicating that 1 in 6 drivers under the age of 25 is involved in an accident annually.
Wait, 1 in 6? That's wild.
1 in 6, compared to 1 in 15 for older demographics.
Wow.
So it's a dramatic statistical cliff. But from the computer's perspective, there is no nuance. It doesn't care if you were 24 and have been driving perfectly since you were 16.
Oh, right. It doesn't care if you are, like, the safest driver on Earth.
And it doesn't care if you were 25 and literally just got your license yesterday.
Yeah.
The logic dictates the branch, and the branch dictates the output. This is where we see the friction between continuous human reality and discrete computational logic. The algorithm requires a hard line to function.
I often think of the basic if-else branch like a bouncer at a highly exclusive yet incredibly literal nightclub.
I like that.
You hand them your ID. That's your input. The bouncer's brain evaluates the expression age greater than or equal to 21. If it returns true, the velvet rope opens, you take the true branch.
You're in.
You're in. If it returns false, you stay on the sidewalk. There's absolutely no room for negotiation. No, like, oh, but my birthday's tomorrow. It's totally binary. But here's my pushback on this model.
Okay.
While that works for a nightclub, human systems are almost never that binary. We don't live in a world of just two paths. When we look at more complex architectures, how do we handle a scenario that requires granular, multi-tiered logic?
Well, that is the defining architectural challenge, isn't it? A single if-else is essentially a toggle switch, on or off. But to model reality, you need a cascade. You need a way to chain these toggle switches together in a way that doesn't, collapse under its own weight.
Right.
This is where we move from a simple branch into an if-else-if structure.
Okay. Let's unpack the if-else-if cascade, because this is where the order of execution becomes super critical. In a visual flowchart, this looks like a waterfall of decision diamonds. And the defining rule here is that a subsequent condition is only checked if the previous condition returned false.
Exactly. It's a process of elimination. The if-else-if cascade is designed for mutually exclusive states. You can only fall into one bucket.
So you can't be in two categories at once.
Right. At the compiler level, once one of those conditions evaluates to true, the instructions for that specific block are executed. And then the processor encounters an unconditional jump instruction that kicks it completely out of the cascade.
Just bypasses the rest.
It explicitly avoids evaluating any of the subsequent diamonds. It drops all the way down to the rest of the program.
Let's trace the anniversary milestone logic from the text to illustrate this mutual exclusivity. So a program takes an input for the number of years a couple has been married. The cascade starts at the top. First diamond years equals 1.
And here we should note the distinction between the equality operator, which is the double equal sign, and the assignment operator, which is just one equal sign.
Oh, that's a good point.
We aren't setting the variable years to 1. We are querying the state of memory. Does the value stored at the memory address for years match the integer 1?
Right. So does years equal 1? If true, it outputs paper. If false, the execution drops down to the next diamond. The else if years equals 25. If true, silver. If false, it drops down again to years equals 50 for golden. And finally, there's usually a catch-all else at the bottom for everything else, like a simple congrats.
Yeah. And if you input 25, let's trace what happens. The first check for 1 fails, the second check for 25 succeeds, it prints silver, and then boom, it jumps entirely out of the structure.
It never even asks if the years are 50.
Never. It's incredibly efficient.
But I want to compare this to another structure, multiple independent if statements. Because if a developer uses the wrong architectural structure here, the logic doesn't just run slower, it fundamentally breaks the real-world application.
Oh, this is a critical distinction. An if-else-if cascade enforces mutual exclusivity, like we said, exactly one block of code will run. But a sequence of standalone if statements enforces cumulative evaluation.
Meaning it checks everything.
Every single condition will be evaluated, independently, regardless of what happened in the previous step.
The age milestones model demonstrates this perfectly. Let's say we want to build a profile of user privileges based on their age. The code is a stack of independent diamonds. Diamond 1, age greater than 15, output can drive. Diamond 2, age greater than 17, output can vote. Diamond 3, age greater than 24, output can rent a car. Diamond 4, age greater than 34, output can run for president.
So if you pass in an age of 35, every single one of those conditions evaluates to true.
Every single one.
The CPU processes the first check, executes the print statement for driving, and then drops right into the next check for voting. It doesn't jump out. The user gets all 4 privileges assigned to their profile.
Now, what happens if a junior developer comes in, looks at that stack of independent if statements, and thinks, oh, I should optimize this by turning it into an if-else-if cascade?
They would completely break the system.
Completely.
If they refactored that into an else-if chain, passing in an age of 35 would hit the first condition age greater than 15. It evaluates to true. The system outputs can drive. And then, because it's an else-if structure, it executes that unconditional jump to the end of the block we talked about.
So the 35-year-old user is never granted the right to vote or rent a car or run for office. They just get to drive.
It's a classic example of syntactic similarity, masking a massive architectural difference. The machine doesn't know what a cumulative privilege is. It only knows what jump instructions you compiled for it.
Exactly. And this brings us to a third architectural pattern that handles a different type of complexity: nested branches.
Right.
If an else-if cascade is a process of elimination, a nested branch is a process of prerequisite triage.
I like that phrasing. Prerequisite triage. Because a nested branch is a completely separate if-else decision that exists entirely inside the true or false path of a parent decision.
So it's a fork you only reach if you've already traversed a specific prior fork.
The amusement park ride matrix from the sources is a great way to visualize this.
Yeah.
You have 2 variables required for Clarence to get on the ride: age and height.
Okay.
The architecture doesn't check them simultaneously. It triages. The first parent diamond checks the most common disqualifier, age less than 10. If that returns true, the ride is over, it outputs too young, and it skips everything else.
But if age less than 10 is false, meaning the rider is at least 10, the execution path flows into a false branch that contains a whole new nested diamond.
Right. It asks a secondary age question, age less than 80. If they're 80 or older, it flags a warning.
Like a heart condition warning or something.
Exactly. But if they're under 80, the path flows into a third nested diamond. Now, and only now, does the system query memory for the height variable and evaluate height less than 48 inches.
From a computational standpoint, this is highly optimized, isn't it?
Extremely. Because querying memory, loading variables into registers, performing comparisons, all of that takes CPU cycles. If a rider is 5 years old, the system never spends the computational energy to check their height. It short-circuits the logic early.
It's just like the architecture of an automated customer service tree.
Oh, a perfect example.
You call in, right? Press 1 for English, you take the branch. Press 2 for billing, you take a nested branch. Press 3 to speak to a human, another nested branch. It's a decision maze designed to route you to a highly specific node by aggressively filtering you out at higher levels.
And while customer service trees are incredibly annoying to deal with,
The worst.
that architectural concept of failing fast and filtering early, that is exactly how high-performance systems process massive data sets. You just don't evaluate complex, expensive logic if a simple, cheap prerequisite fails.
Okay, so we have cascades for mutual exclusivity, we have independent conditionals for cumulative states, and we have nested branches for prerequisite triage. But the actual logic inside these diamonds, the rules we are enforcing, relies on how we draw the mathematical boundaries. And this is where I want to debate the concept of implicit ranges.
Okay, let's get into it.
Because when we talk about relational operators, the less than and greater than checks, we see a technique in the text that feels very elegant, but also incredibly dangerous.
You're referring to using an if-else-if cascade to establish a floor without explicitly coding it.
Exactly. Let's look at the youth soccer league model. The club assigns kids to divisions under 8, under 10, and under 12. The code is an else-if cascade. The top diamond is age less than 6. If true, it says no teams, too young.
Okay.
The next diamond is age less than 8. If true, U8 team. The next is age less than 10 for U10, and so on.
Right. It's standard top-down range logic.
But look at that second diamond, age less than 8. If you look at that Boolean expression in absolute isolation, a 4-year-old fulfills the condition. 4 is less than 8.
It is?
So why doesn't a 4-year-old get placed on the U8 team?
Because of the state of the cascade. By the time the instruction pointer reaches the age less than 8 evaluation, the system inherently knows that the age less than 6 evaluation returned false.
Oh.
If the child were 4, the first diamond would have caught them, and the LSIF jump would have bypassed the rest of the cascade entirely.
Right, so the mere presence of the execution marker at the second diamond implicitly establishes a floor.
Yes.
The system knows the age is at least 6. The programmer didn't have to write, is the age greater than or equal to 6 and D less than 8. They just wrote age less than 8. The architecture itself acts as a sieve, catching the smallest particles first and letting the larger ones fall to the next layer.
It's the DRY principle in action. Don't repeat yourself.
Right.
It keeps the code base clean, it reduces the number of operations the CPU has to perform, and honestly, it is generally considered elegant syntax.
But here's my pushback.
Yeah.
Isn't this just lazy coding that creates a massive architectural vulnerability?
Yes, ma'am.
It relies 100% on the structural sequence remaining perfectly intact. What happens in a large legacy code base when a developer is tasked with adding a new under 12 division and they accidentally insert that check at the top of the cascade before the under 8 check?
Oh, well then the logic collapses catastrophically.
Right.
If the top diamond is aged less than 12 and you pass in a 7-year-old, that evaluates to true. The 7-year-old is placed on the U12 team, and the cascade bypasses the age less than 8 check entirely.
It just swallows everything.
Exactly.
Yeah.
The narrower conditions are completely starved of inputs because a wider net was placed above them.
So in high-stakes environments, let's say an algorithmic trading platform determining trade volume tiers, or a medical device calculating dosage based on weight brackets relying on the physical sequence of the code to implicitly define your boundaries, seems reckless. Why not just be explicit every single time to prevent a refactoring error from causing a disaster?
Well, you're touching on a massive debate in software engineering regarding maintainability versus safety. You are right that explicit boundaries are safer against human refactoring errors. But explicit boundaries require logical connectors, the AND and OR operators, which introduce their own complexities and computational overhead.
Okay, fair.
There are times when implicit cascades are preferred for performance. But as you correctly point out, there are times when explicit ranges are absolutely mandatory because the data itself has gaps.
Let's explore that. When do we absolutely have to abandon the implicit cascade and use explicit logical connectors?
We use explicit ranges when the logical buckets aren't perfectly contiguous. The models use a great example of a cable television provider assigning channel packages.
Oh yeah, the TV channels.
Right, so the standard package includes channels 2 through 499. The high-definition package includes channels 1002 through 1499.
Notice the massive dead zone in the middle. Channels 500 through 1001 don't exist in either package.
Exactly. So if you try to use an implicit ELSIF cascade here, it fails.
Yeah.
If you write, if channel is less than or equal to 499 output standard, ELSIF's channel is less than or equal to 1499 output high def. What happens if a user inputs channel 600?
The first check, less than or equal to 499, returns false. So the cascade drops to the next check, less than or equal to 1499. Is 600 less than 1499? Yes. So it outputs high def.
Which is wrong.
It's totally wrong. The implicit logic falsely assumed that anything failing the first check was valid for the next tier. It didn't account for the void in the data.
To fix this, you must construct an explicit range using a logical AND operator. You force the computer to simultaneously evaluate the floor and the ceiling. The expression becomes channel greater than or equal to 1002 AND channel less than or equal to 1499.
So both operands must resolve to true for the entire expression to return true.
Right.
If the input is 1100, 1100 is greater than or equal to 1002, that's true. 1100 is less than or equal to 1499, that's true. True and D-true equals true.
But if the input is 600, 600 is greater than or equal to 1002, that is false. And at this exact moment, modern compilers do something incredibly clever called short-circuit evaluation.
Oh, this is fascinating. Let's dig into short-circuit evaluation because it really speaks to how hardware optimizes these logical constructs.
Yeah. If the computer is evaluating an AND expression, it knows that both sides must be true, so it evaluates the left side first. If the left side returns false, the entire expression is mathematically guaranteed to be false, regardless of what is on the right side.
Right, there's no way to salvage it.
Exactly. So the processor doesn't even bother evaluating the right side. It short-circuits the operation, saves the CPU cycles, and moves on.
So in our channel 600 example, it checks 600 greater than or equal to 1002. That's false. It immediately abandons the rest of the statement. It doesn't even check if 600 is less than 1499.
Yeah.
That is incredibly efficient.
It's not just for speed, though. It's actually a critical safety mechanism. Programmers use short-circuiting to protect the system from crashing.
Really? How so?
For instance, you might write an expression like, if data exists equals true, A and D, data value is greater than 50. If data exists is false, it short circuits. If it didn't short circuit, and it tried to evaluate data value greater than 50 on data that literally didn't exist in memory, the program would throw a null reference exception and crash entirely.
That's brilliant. The architecture uses the logical connector not just for Boolean math, but as a protective barrier. Now, contrast that with the logical OR operator, which only requires one operand to be true.
Short-circuiting happens with OR as well, just in reverse. If the left side of an OR statement is true, the whole statement is guaranteed to be true, so it ignores the right side.
But the OR operator highlights a funny friction point between human language and Boolean logic. We use OR very loosely.
We do.
Like, if a host at a dinner party says, "Would you like wine or water?" they usually mean an exclusive OR, one or the other, not both. But in Boolean logic, if both operands are true, an OR statement happily evaluates to true. If I tell the system I have wine A and D water, the OR condition is satisfied. It requires a terrifying literalism that human language just doesn't possess.
Humans rely on context. Computers rely on operators. And the complexity really compounds when we start mixing these operators together. When you have A and D, or not, relational operators, and arithmetic all in a single expression, the compiler has to figure out exactly how to deconstruct it.
Which brings us to the precedence tree, order of evaluation, because if you don't intimately understand precedence rules, you will write code that compiles perfectly, runs without crashing, and quietly outputs completely catastrophic logic.
And a logic bug is infinitely more dangerous than a syntax error, because the machine won't warn you. It just perfectly executes your flawed instructions. Precedence rules are the unyielding hierarchy of operations. When a compiler looks at a complex string of text, it parses it and builds an abstract syntax tree, or AST.
A literal tree?
Yes, constructs the literal tree data structure from the bottom up based on this hierarchy.
Okay, let's review the hierarchy from highest priority at the top to lowest priority at the bottom.
Okay.
Priority 1, parentheses. Always evaluated first. Priority 2, logical not fin, the inverter. Priority 3, arithmetic operators. Standard math, multiply, divide, add, subtract. Priority 4, relational operators, less than, greater than, etc. Priority 5, equality operators, equals and not equals. Priority 6, logical A and D. And priority 7, dead last, logical OR.
Let's trace how the compiler builds an AST for a complex, unparenthesized expression from the models. X plus 1 is greater than Y times Z OR Z equals 3.
Just reading that out loud feels like a jumble. X
Yeah.
plus 1 greater than Y times Z OR Z equals 3. Let's give them values so we can track it.
Sounds good.
Let's say X is 7, Y is 6, and Z is 3.
The compiler scans it and finds the highest precedence operations. There are no parentheses, no not Z's, so it finds the arithmetic, X plus 1 and Y times Z. These become the leaf nodes at the very bottom of the AST. It executes them first. 7 plus 1 becomes 8. 6 times 3 becomes 18.
Okay, so the string simplifies in memory to 8 is greater than 18 OR Z equals 3.
Next on the hierarchy are relational operators. It finds the greater than sign. It evaluates 8 greater than 18. This returns false. That entire left branch of the syntax tree collapses into the single Boolean value false.
Got it. So the string is now false, OR Z equals 3.
Next is equality. That evaluates Z equals 3. Since Z is 3, this returns true. The right branch of the tree collapses to true.
Which leaves us at the root node of the tree, the final evaluation false or true.
And since it is an OR operator and the right side is true, the entire expression evaluates to true.
It's so satisfying to watch the engine break it down like that. But looking at the precedence list, I have a fundamental question about the architecture. Why is the logical OR at the very bottom? Why does it have the absolute lowest priority of all the operations?
Because OR is the ultimate boundary between disparate universes of logic.
What do you mean?
Think of it like a military command structure, or a chef preparing a highly complex dish. The chef doesn't mix raw flour and underdo stock together. The precedence rules force the system to fully resolve all the local operations first. You reduce the sauce on the left side of the kitchen until it's a finished product. You roast the meat on the right side until it's a finished product. You evaluate all the math, all the relations, all the A and Ds, reducing massive blocks of code down to a single true or false state.
Right.
Only then, at the very end of the process, does the OR step in to evaluate the finalized states. If OR had a higher precedence, it would start prematurely linking unresolved mathematical operations together, creating total logical chaos. or is the final arbiter.
That makes perfect sense. The OR is the final judge. Did either side of the room survive the gauntlet? Let's look at a real-world architectural design that leverages all of this. The toll booth calculation model from the text. It combines implicit cascades, explicit logical ranges, and nested branching all into one cohesive system.
Toll calculation is a classic problem of state management. The price changes based on the time of day, but there are also overriding modifier states, like whether the vehicle is a high-occupancy carpool.
Okay, let's define the base states first. The timeline is broken into 4 buckets using a 24-hour clock. Before 6:00 a.m., the toll is $1.50. From 6:00 a.m. to 9:59 a.m., the morning rush, it spikes to $4.60. From 10:00 a.m. to 5:59 p.m. or 17:59, it drops to $2.30. And 6:00 p.m. onwards, it returns to $1.50.
The architecture handles this baseline timeline with an elegant, implicit LCF cascade. First diamond time less than 6, toll is 1.50. Next diamond time less than 10, toll is 4.60. Next time less than 18, toll is 2.30. Else toll is 1.50.
It's clean.
Very clean. It's mutually exclusive, and it relies on the execution sequence to establish the implicit floors for each time bracket.
But the base toll is only step 1. Now the system has to process the modifier. The carpool discount. The rules dictate that if a car has 3 or more people, they pay absolutely nothing. Free. Unless they're traveling during that specific morning rush hour window, 6:00 a.m. to 9:59 a.m. If they are in that window, the carpool discount is modified. They have to pay half the base toll.
This requires a structural shift. The instruction pointer exits the cascade and hits a completely independent if statement to check for the modifier state occupants greater than or equal to 3. If false, the program ends and you pay the base toll.
Right.
If true, you enter the carpool logic branch, and immediately you hit a nested decision diamond.
And what is the expression inside that nested diamond?
Well, the system needs to know if the current time falls inside the morning rush hour.
Wow.
But wait, didn't we already establish the time brackets in the cascade above?
Yes, but the system doesn't remember the logic of the cascade. It only remembers the final variable it set. The context of the implicit range is completely gone.
Exactly.
So here, inside the nested branch, the developer is forced to use an explicit range with a logical connector. The expression must be time greater than or equal to 6a and d time less than 10.
You cannot rely on an implicit boundary in isolation here. The nested branch evaluates both the floor and the ceiling. If the expression returns true, meaning, yes, it is morning rush hour, the true path executes, and the toll equals toll divided by 2.0. If it returns false, the path executes toll equals 0.0.
It is a phenomenal example of architectural synthesis. I mean, you use the fast, implicitly bounded cascade for the broad time triage, you use an independent branch for the state modifier, and you use an explicitly bounded logical A and D statement inside a nested branch to handle the exception to the modifier. When you map it out, it's a beautiful machine.
It is. But it's also a machine that requires absolute syntactic precision because the compiler will not save you from your own logical assumptions. A common devastating mistake junior programmers make when trying to build these explicit ranges is writing them as if they were doing algebra on a chalkboard.
Right. Writing 0 less than x less than 10 without any parentheses or logical AND operators. We know we should write 0 less than x, AND x less than 10. But what actually happens at the hardware level? If a programmer just types 0 less than x less than 10 in a language like C or C++ that allows it to compile?
Oh, this is a perfect storm of precedence rules causing silent failure.
Let's trace it.
Let's say x is 5. We want the expression to return true. The compiler evaluates relational operators from left to right. It looks at the first part, 0 less than x. Is 0 less than 5?
Yes.
It evaluates to true.
Okay, so far so good.
Now, at the machine level, Boolean values are frequently stored as integers. True is 1, false is 0. So that first evaluation, true, literally becomes the integer 1 in memory.
Wait, really?
Yes. Now the compiler moves to the second half of the expression. It takes that result, 1, and compares it to the rest of the string less than 10. It evaluates 1 less than 10. Is 1 less than 10? Yes. It returns true.
Okay, wait. The program got the correct answer. It returned true for 5.
It got the right answer for the completely wrong reason. The danger becomes apparent when you change the input. Let's say x is 20. 20 is not between 0 and 10. So the expression absolutely must return false.
Okay, let's trace it for 20.
Left to right, 0 less than 20 is 0 less than 20. Yes, it evaluates to true.
Oh no, I see the trap.
The true is cast to the integer 1. The compiler takes that 1 and evaluates the right side, 1 less than 10. Is 1 less than 10? Yes. It evaluates to true. The system returns true for 20. The system will return true for 1,000,000. It is a massive logical collapse, all because the developer didn't use an explicit logical connector, and the compiler blindly followed its left-to-right evaluation precedence.
That is terrifying. It's the ultimate manifestation of architectural literalism. The computer did exactly what you told it to do, which was compare a Boolean integer to the ceiling value.
And this brings us to the most profound and frankly unsettling realization about this entire architecture. Up until now, we've been assuming that if our logic is perfectly found and our syntax is flawless, the machine will perfectly execute our will. But that assumes the physical hardware of the machine is capable of perfect mathematics. And it isn't.
Which leads us to the final concept we need to unpack, the intersection where pure theoretical logic crashes into physical reality. We are talking about floating point architecture and why you can never entirely trust a computer with a decimal point.
It is the great humbling of computer science. The models include a massive bolded warning. Floating point types, meaning numbers with decimals, should never be compared using the equality operator. You should ever write an expression that asks x equals 3.14.
Why not? If I assign x equals 3.14, why can't I ask if it equals 3.14?
Well, understand why. You have to look at how numbers are stored physically on a silicon chip. We do math in base 10. Computers do math in base 2 using binary. When you assign an integer, like 5, it maps perfectly to binary. But when you assign a fraction, a decimal, the computer has to approximate it using a standard called IEEE 754 floating point architecture.
Let's break that down. How does the architecture attempt to store a decimal?
It splits the physical memory allocated for that number, let's say 64 bits, into a sign bit, an exponent, and a mantissa, which is the significant digits. It tries to represent the decimal as a fraction of powers of 2, halves, quarters, eighths, sixteenths. But just like the fraction 1/3 cannot be written perfectly in base 10 decimal, it's 0.333, repeating infinitely many clean base 10 decimals cannot be written perfectly in base 2.
So they have an infinite repeating pattern in binary.
Exactly. A number as simple as 0.1 has an infinite repeating pattern in base 2. But the hardware doesn't have infinite memory. It only has 64 bits, so it has to physically chop off the end of the number. It truncates it. What is stored in memory isn't exactly 0.1. It is an incredibly precise approximation that is infinitesimally off.
The models demonstrate this with a terrifyingly simple math glitch. A developer writes a program, they set a variable meters equals 0.7. Then they write an instruction to subtract 0.4. Then they subtract 0.3. In human, base 10 math, 0.7 minus 0.4 is 0.3. Minus 0.3 is exactly 0.
But look at the actual output of the Coral simulator's memory state after those operations. The value stored in the meters variable is not 0.0. It is negative 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000
That is an absurdly tiny microscopic fraction of a negative number. It's structural noise generated by the base 2 approximation errors compounding during the subtractions.
But it's not noise to the CPU. It is the literal physical state of the transistors holding that variable. So if the very next instruction of the program is a decision diamond that asks if meters equals 0.0, what happens?
The processor pulls the value from memory, looks at negative 0.000 whatever, compares it to exactly 0.0 and says, these are not identical. The expression resolves to false.
And your logic branch fails. If this is a banking application reconciling a ledger, the ledger fails to balance. If this is a guidance system for an orbital thruster aiming for a zero-velocity docking, the thruster keeps firing because it thinks it hasn't reached zero yet. The pure, perfect logic of the flowchart is betrayed by the physical limits of the silicon holding the data.
It's like a carpenter trying to build a table. They use a standard tape measure, mark a piece of wood, cut it, and say, that is exactly 10 inches. But then the computer walks into the wood shop with a scanning electron microscope, zooms in on the jagged atoms of the saw cut, and starts screaming, system error! This is 10.00000000001 inches. It is not 10.
Right.
The computer is having a logical breakdown over atomic level variance. So how do we fix this? We can't just build infinite memory. How does an architect force the system to calm down and accept the reality of the wood?
We have to explicitly program forgiveness into the architecture. We have to create a mathematical threshold of tolerance. In numerical analysis and computer science, this buffer is called an epsilon.
The epsilon fix. How do we implement it in a logic diamond?
We abandon the equality operator entirely when dealing with floating point numbers. Instead of asking if two numbers are exactly the same, we ask if the difference between them is smaller than our acceptable margin of error, our epsilon.
The formula in the models is elegant. You subtract the two numbers to find the difference. Because the error could be slightly positive or slightly negative, you wrap the subtraction in an absolute value function. So it looks like absolute value parentheses meters minus 0, 0, 0.
That operation yields the microscopic variance. In our example, it drops the negative sign and returns 0.000000000000000000000000000001. The final expression inside the decision diamond because absolute value of meters minus zero point 0.0 is less than 0.0001. The processor evaluates it. Is that massive string of zeros less than 0.0001? Yes. The expression resolves to true.
Sure.
The computer effectively says, I can see with my electron microscope that these are not identical, but the variance is within the predefined threshold of tolerance. I will evaluate them as functionally equal. The execution takes the true branch, and the system survives. By manually inserting an epsilon, we bridge the gap between theoretical logic and physical hardware limitations.
It's a profound architectural compromise. I mean, we spend all this time building these rigid, unyielding cascades, enforcing mutual exclusivity, relying on the terrifying literalism of A&D and OR connectors. But at the very foundation of the mathematical computations, we have to engineer a buffer of close enough.
Because without that buffer, the continuous nature of reality cannot be mapped onto the discrete nature of a binary machine. The architecture would paralyze itself, seeking an impossible perfection.
This has been a massive paradigm shift. We started by looking at a simple fork in the road, the if-else branch. We examined the architectural differences between mutually exclusive else-if cascades and cumulative sequential conditionals. We explored how the structural sequence of the code implicitly defines boundaries and when we're forced to explicitly define them to prevent catastrophe.
We unpacked the compiler's precedence tree, understanding why local mathematical operations must be resolved into binary states before the logical OR acts as the ultimate arbiter.
And finally, we confronted the physical limits of floating point memory and the necessity of the epsilon to grant the machine a margin of forgiveness. It fundamentally changes how you view the digital infrastructure. The next time you see a dynamic price shift on an airline ticket or you get routed through a phone tree, you aren't just experiencing an outcome. You are a data point being pushed through an invisible, microscopic architecture of diamonds and branches.
You are interacting with millions of cascading logic gates, optimized by compilers, short-circuiting for efficiency, and buffered by epsilons to keep the whole fragile, beautiful structure from crashing. It is the mechanics of the modern world.
But I want to leave you, our listener, with a thought that extrapolates this computer science concept into our own wetware, our own human operating systems. We just spent this entire deep dive analyzing how computers are the ultimate engines of literal, uncompromising binary truth. True or false, 1 or 0. Yet, we discovered that at the deepest, most foundational level of their processing, to make the entire rigid system actually function in the real world, architects had to invent the epsilon. They had to mathematically encode a threshold of tolerance, a structured acceptance of close enough, simply to forgive the unavoidable physical imperfections of the machine's own memory.
If they demand absolute atomic level equality, the logic fails and the system breaks.
Exactly. So if the most literal deterministic binary machines in human history require an epsilon just to survive, what does that say about us? When we are evaluating conflicting ideas or arguing over rigid ideological rules or dealing with people who don't fit perfectly into our own implicit mental cascades, maybe we are crashing our own systems by demanding atomic level perfection. Maybe the most advanced logic we can apply is to consciously program a little epsilon into our own minds, a threshold of tolerance to accept the tiny structural imperfections in our reality so the system can keep running.